Now, how these charges behave is actually interesting. So, much like people. So, if you stick two positive people in a room, they're not going to have much to talk about. They're both just going to talk about how life is swell, but they'll get bored very quickly, and there'll be no chemistry between them. So they're going to go away pretty fast. So much like that, positive charges don't usually attract. They just repel each other and go away. Similarly, to depressed, miserable people are not going to want to hang out with each other for too long. They're also going to kind of leave each other alone because they already have enough sadness as it is. So, but if you then put a positive person and a negative person in a room together, the positive person is going to find his perspective interesting, and the negative person is going to find his perspective interesting. So the positive, being the more extroverted, is going to want to come to the negative. And the negative charge is not really going to dislike that. So they will both attract. Right? So this is just the fundamental behavior of particles. Positives repel, negatives repel, opposites attract. Okay, so now, because we know that these repel, these attract, there has to be some sort of force that is bringing them together or pulling them apart, right? Because if there was none, they would just stand still. Much like in human interactions, if you're repulsed by someone, you are going to exert a lot of force to get some distance, right? If you're super repulsed by them, you might run away, which is going to exert a lot of force from you. If you're attracted to someone, you're going to put a lot of effort, a lot of force into being close to them. So there has to be a force that is pushing these particles together or apart. So a charged body, even if it's just one of them, can exert forces on someone that's uncharged. So if a particle is completely neutral, like we discussed here, if the number of protons and electrons is the same, a charged particle, if it is charged strongly enough, can still put some force into it because a particle can never be 100% fully neutral. Yeah, there's always going to be little factors that will factor in the charge of the particle. So, Coulomb, my man, Coulomb discovered that these forces, the strength of these forces, depends on, so this is the same, proportional to, depends on the charge, so how many electrons are present, right? So if there's going to be more electrons, or rather if there's going to be a bigger difference, so if this one is going to have a tiny amount of extra electrons and this one is going to have a ridiculous amount of electrons, the force will be stronger than if they have almost a similar amount of electrons. If this one might just have a few less, that makes it positive, and this one has a little bit more, that makes it negative, right? If they have a huge difference between them, they're going to be really attracted to each other because opposites attract. So it's proportional to the charge. So the bigger the charge difference, not just the charge, the bigger the charge difference, the larger the force. The strength is also inversely proportional to the distance. So if these two charges happen to be a huge amount apart, the force that can act between them will also be weaker because it has to act over a longer distance. Yeah? So the smaller the distance, the more they attract. Yeah? Until they collide. So that makes sense. Therefore, his equation for this was force equals the product of two charges over the distance squared. So because it's inversely proportional to the distance, 1 over r2, and proportional directly to the charges. Yeah? And this just means that whatever you get out of that is going to be positive. So even if you have a negative result out of these two, it needs to be turned into a positive. Because, well, force is a vector, which means it has magnitude and direction, but this equation is working out the magnitude. You then have to work out the direction and decide whether it's a positive or a negative yourself. We'll get to that. Just stick with me. So the magnitude is equal to the product of the charges, charge 1, charge 2, charge 1, charge 2, divided by the distance between them, and then multiplied, and this is a constant, so this one doesn't really change as long as you have the same material that it's going through, right? So if you have air that these charges are traveling through, if you have cloth, water that these charges are traveling through, this constant is just going to change based on material. And it is 1 over 4 pi, and then this weird E letter. So in this case, we can say Q1, Q2 is the charges, and they're measured in coulombs, right? So that's coulombs is just the unit for how many electrons there are altogether, yeah? And you can obviously see that the bigger the charge number will be, the more electrons there are, the higher the attraction. The bigger the electron number is, the larger the cloud, which means that there's more force that they can put onto each other. R is just the distance in meters, and this weird E letter is the permittivity, which is what we're going to get into now, okay? But the one thing that you need to make sure is, so from left to right is usually a positive direction. From right to left, usually a negative direction. Force is a vector, which means that it needs to have size and direction. This will give you the size, the magnitude. You have to work out the direction it's going into.